Now that we are more seasoned, we will meet directly at the gates to hear our new mission from Kakashi-sensei. Kakashi states, the Hokage has given us our third mission, folks. It is varied and could be B rank up to S rank, depending on the surroundings. The goal of this mission is to gain knowledge about primary batteries and their applications by traveling to the hidden primary battery village in the Land of Sound. So we are here and we'll be going straight up to the hidden primary battery village. Now, the hidden primary battery village has not always had the best reputation with our village, but we are still going to be on a mission to learn. We will not be learning any particular jitsu, but we will gain critical thinking strength by making connections with our general understanding of a voltaic cell. Now, the overall idea is to save all of our energy for the Chunin exams in the Land of Earth at the hidden electrolytic village. This is where our battle/examples will take place. So let's get it, folks. We arrive to the hidden primary battery village, greeted by the master manipulator himself, Orochimaru. Now, Orochimaru is known for his pursuit of immortality and mastery of forbidden jitsu techniques. He studied primary batteries and is willing to provide information and allow some of his subordinates to help for a price. And that price is that he wants to learn the Vulture Seal Jitsu. So Kakashi reluctantly agrees, and Orochimaru states, batteries are crucial in daily life due to their compactness and mobility. And a typical battery consists of a self-contained voltaic cell arranged in a series of plus minus, plus minus, plus minus, so that their individual voltages are added up. So just imagine a bunch of these voltaic cells all coming together with their own individual voltages. And all those voltages are added up to get a total voltage of, say, like 1.5 volts, which we normally see for a typical alkaline battery, right? Like Duracell, for example. And so that 1.5 volts are in that Duracell battery. And then once that 1.5 volts have been used up, then the battery is dead. It's no longer usable, for example. Now, there's actually 3 categories of batteries we're going to talk about overall, and that is primary batteries, secondary batteries, and fuel cells, also called flow batteries. But for this village, our focus is going to be the primary battery, okay? Orochimaru then states, primary batteries cannot be recharged, and their initial reactance amounts are set far from equilibrium. So we call this whole thing primary non-rechargeable batteries, okay, folks? And the non-rechargeable part comes from the fact that the overall voltage is going to be set very, very high, that 1.5 volts, so you have a lot of reactance. And then over time, the non-standard E of the cell is going to keep decreasing until it gets to 0. Once it hits 0, then we know that that battery is considered dead and can no longer be used. Okay, folks? Orochimaru continues. There are 3 specific types of primary non-rechargeable batteries that he's willing to discuss with us. The first is going to be alkaline batteries, and then there also are silver button batteries. And then finally, there is the primary lithium battery. Orochimaru is going to start with the alkaline battery, and he states that alkaline battery is a dry cell battery. And this means that it contains a paste form of the electrolyte versus a liquid form. So in an overall voltaic cell, we know that the electrolytes are usually ions in solution, like we have zinc 2+ here and copper 2+. But for an alkaline dry cell battery, this overall electrolyte solution is in a paste form. And for the alkaline batteries here, that paste form is going to be KOH and water. And so it's like this basic mixture that is used as the electrolyte solution. Remember, when we are taking our understanding of this voltaic cell here and seeing how it relates to several applications like the alkaline battery, we often are looking for key parts that function as the cathode, key parts that function as the anode, the electrolyte solution, and of course the circuit itself, meaning the salt bridge or something to separate the 2 half cells, and then something that is going to capture the voltage between the cathodes as well. Applying that to an alkaline battery, we often see this entire type of voltaic cell, or the cathode and anode and the separator, etc., in this form. So for this Duracell battery, it's kind of like we have taken a piece of it or a fourth of it. You see that this tiny little sliver here is actually the separator, acting as the salt bridge, okay? And it also is porous enough to actually have the electrolyte solution within it as well. And so you'll see it just be called the porous barrier, and that just means it's a separator and the KOH and water paste, okay, for the electrolyte. And then, of course, we're going to have the cathode, which will be represented here. This is the cathode, and of course, I kind of tried to call it out as yellow here, this portion of the cathode as well. And again, this is a separator. And so if this is the cathode separator, that means this must be the anode. And so the question becomes, where is the circuitry portion as far as where is the voltage going to come in at? Well, here is the collector here. It's kind of like a little portion that all the electrons are going to collect to so that we can get our overall output of voltage for this battery. At the cathode here, we see the reduction of manganese dioxide that is mixed with graphite. And so we know graphite is going to be that carbon, right? Solid carbon. And then the anode is actually a powdered zinc in a gel form. And that is going to be the half reaction that we see here. So we are losing 2 electrons that is going to be gained here by the manganese dioxide. And so the overall cell reaction is what we see here, zinc solid, the manganese dioxide solid, and plus liquid water is going to give ZNO solid plus MnOH2 solid. And they give us an overall non-standard cell potential of 1.5 volts. So we're again going to start with the 1.5 volts. That's going to be used to power calculators or remote controls, flashlights, toys, right? Game controllers, wireless mouses, etc., etc. So all that 1.5 volts is used to power all these things until one day you pick up your remote control and of course it does not work anymore, right? Because E of the cell has gotten to 0 and now the battery is dead. So look how useful it has become to daily life. Also, look how easy it is to just go and pick up a pack of these batteries and just carry them around in your pocket anytime you need them. So these alkaline batteries are safe. They come in various sizes. You don't have any issues with voltage drop, meaning you're not going to use it one day and then all of a sudden one day it doesn't work. No, you're going to use it until it gets used up, right? And then also it has a pretty good shelf life. You can go ahead and create an emergency preparedness kit for yourself and put some batteries in there and replace them every couple of years, for example. And there are even some alkaline batteries that can last 5 to 10 years depending on use. Okay, so this is all the information Orochimaru is willing to give. He then says his subordinate Kabuto will tell us more. Let's go to Kabuto. Meet Kabuto, Orochimaru's right-hand man and also a fellow experimenter and medical researcher. I am making these villains look really nice here, right, folks? The people who really follow the Naruto story know that these are some of the villains, but they're also some of my favorite characters, so I am jazzing them up a bit. Either way, Kabuto is definitely going to be someone who follows the orders of Orochimaru, and so he's going to let us know about the silver button battery. Now, you could just say it's a silver battery. We say silver button battery because a lot of them are made as these small little silver buttons. Same one we see in our timers, our watches, same ones we're going to see in some cameras, for example, and even hearing aids. Kabuto states, a silver button battery typically uses a zinc silver oxide chemistry. So the anode is going to be made of zinc. Of course, the cathode is going to be made of a silver oxide. And the electrolyte is a gel. And that's usually going to be a basic medium, and it's usually going to be, again, the KOH gel here. Now, the zinc is going to be compacted with the KOH gel for the anode portion. And I didn't say this before with the alkaline battery. You know, usually you have the Duracell batteries here. You have the positive and the negative based on where the cathode and the anodes are placed. And so a lot of times you usually see these portions be capped. And they're just capping those areas where there is those negative and positive charges. So the cap here for the silver button batteries is going to be the anode cap for the negative portion coming from the anode, and the positive cap that we can't see here, which is going to just cover the overall cathode portion. So our anode, again, is going to be zinc. That's going to be compacted with this KOH gel. And then our cathode is going to be pellets of that silver oxide, and that's going to be compacted with graphite. Now, we also do have a separator that is simply going to be a porous filled membrane and also a gasket above it that's going to help keep the voltage stable. Now, the electrons for the silver button battery are going to be collected at the anode, okay, folks? And so we can actually look at the anode oxidation. We have our solid zinc, of course, is going to be packed with that KOH, and it's going to form a ZNO solid and water, and of course, release those 2 electrons. At the cathode, we're going to have our silver oxide, going to have a little bit of water added. It's going to gain those electrons and form silver solid and release the OH minus. Now, the overall reaction is here with a non-standard cell potential. Now, technically, again, these are called silver batteries, but they are usually manufactured as button-sized batteries, so we call them the silver button battery. And they're going to be used in watches, as we see here on the screen. Okay, so we're going to take the anode side that has that 1.6 volts and put it in upside down to provide the energy or power to power this watch. Okay, folks. Now, it also have the ability to power cameras, heart pacemakers, hearing aids, timers in the lab, and more. Kabuto then continues and says that this battery also has a very steady output of the 1.6 volts over about 5 to 7 years. Of course, it really is going to depend on what you're using the battery for, right? But the reason why folks don't really like to use a silver button battery is because it is made of silver, which can be very costly for different manufacturers. Okay, folks? Just keep that in mind. So what do you do instead? You use other batteries that are more efficient to power whatever you're trying to power. That's it. Now, Kabuto wants to get back to his research, so he orders Kimimaru to finish the last primary battery explanation. In comes Kimimaru, feeling threatened by our presence already, but a very loyal follower of Orochimaru and willing to give his 2 cents. He states, the last type of primary battery I'll tell you about is the primary lithium battery. Now, primary lithium batteries are non-rechargeable batteries that use lithium as the primary component in both the anode and the cathode. This is going to provide a high energy mass ratio and of course allow the primary lithium battery to have a very long shelf life. We're talking upwards of about 10 to 12 years, folks. Now, these primary lithium batteries are going to be widely used in watches. They're also going to be used in medical products like the heart pacemaker, and they're also going to be used in remote control devices, some calculators, and even more things, right? And so you start to have to ask yourself, wait a minute, I thought that the silver button batteries or the alkaline batteries could be used for those things. Guess what? It's all about what's going to give you the most efficiency for what you're trying to do. So for a heart pacemaker, using a primary lithium battery might be more efficient than using a silver button battery, and it for sure will be more cost effective. All right, let's go ahead and talk about why. Well, the primary lithium batteries have a high energy mass ratio. So the mass of lithium is going to come from the periodic table. It has a molar mass of 6.941 grams per mole. And for every 1 mole of lithium, you actually produce 1 mole of electrons, or 1 Faraday. And so because of that high energy mass ratio, it's another reason why using the primary lithium battery is going to be way more cost effective. It's going to allow us to have way better energy storage and operate at a lower rate, way over the silver button battery as well. Now, the anode is going to be kind of the red portions here. You can see that. And that is going to be our lithium. That is going to be lithium foil and a non-aqueous electrolyte. And then you also have the cathodes here. So let's find one of the cathodes here, which is going to be in the green portions here. And that is going to be metal oxides with lithium. Okay, so it's really going to be lithium ions between oxide layers. So for this example on the heart pacemaker, the silver vanadium oxide is what's going to be used. That's what SVO is, silver vanadium oxide. You'll see it here, silver vanadium oxide. And again, that's going to be our cathode. And so, of course, we have to be like, where's going to be our separator? Our separator is going to be the yellow portions here, and that is going to include any type of electrolyte that might be missing in the overall circuit, anything that's necessary to complete the overall voltaic cell. We can go further and get the anode for this overall pacemaker and for this overall battery, which is going to be that solid lithium, forming 3.5 electrons that are going to be released in oxidation. And then you have cathode here, which is going to be our SVO cathode, or our silver vanadium oxide here, that is going to gain those 3.5 electrons. And of course, the overall cell reaction is here. Now, you might not see a voltage because the voltage does have a range. It can provide a range of 1.5 to 3.5 volts of power for these different primary lithium batteries. Some might then ask, well, why is there a range? And it has to do with the limited energy storage based on the fact that we're using the lithiums and kind of separating them in this exact way, okay? So it has to do with the configuration and how it's made, all right, folks? Now, we know that due to limited energy storage, it is going to operate at a lower rate. And so that can be an advantage for someone with a heart pacemaker. You want the battery to last for a long time, and you want it to last and it be very steady, right? So this heart pacemaker, for example, will continue to have an output of 1.5 to 3.5 volts, or whatever is necessary for that overall reaction to take place to help that particular patient. All right, all of a sudden, Kimimaru then pulls out a piece of bone and orders us to leave. He doesn't want to talk to us anymore. So we square up for the tussle, but realize we need to get our mission done. So our time in the Hidden Primary Battery Village is definitely over. We head back to the Hidden Chemistry Village to review our findings, make connections to voltaic cells, and what we know. Our critical thinking skills have increased, folks. We are ready to head back to the gates for another mission.